Hello everyone. This is Ankit. First of all, welcome to this session. In this session, we will be discussing about streamlining event-driven API design. So, under this topic, we will be primarily talking about the power of async API and how it can help you automate your infrastructure deployments. What are the challenges with this approach, and what are the possible solutions to address those challenges? What is the production readiness of the solution? Because to get serious with any solution, to move it to a production level deployment, we have to understand that if the solution is has already addressed all the production challenges and so on. And we will end this presentation with a demo to help you understand how effective it is to have async API spec and use that to automate your infrastructure deployments. So before we dive in, I'll start by introducing myself. My name is Ankit, and I work as head of developer and customer success at Aklivity. We specialize in streaming and API infrastructure. So a quick shout out to Async API community for giving me this opportunity to share my experience. At Aklivity, we are a huge fan of Async API movement. We have done some work to add coverage for servers and events to the Async API spec. Now, coming to the power of Async API, Async API has evolved into this industry standard for all our event-driven architecture use cases. Its protocol agnostic approach helps us accommodate all the EDA solutions with complex and multi-protocol architecture. As you can understand, to build a EDA solution, it's almost certain that you have to involve multiple different protocols like HTTP, Kafka, MQTT, and so on. So thanks to the Async API's coverage of all these different types of protocol, it can act as a single source of truth for both your documentation implementation, and thus eliminating the chance of drift between both. Which what that basically means is, let's say you get started with a you get started with designing your event-driven APIs, and once you have the initial draft ready, you can use that async API spec to actually deploy your infrastructure. And in future, if you want to make any changes to the spec, it will auto deploy the new configuration instead of maintaining two separate source of truth for documentation or for design and again for the implementation. Async API spec enables us to kind of have a single source of truth, thus avoiding the drift that happens between the design documentation and also the implementation. So what are the advantages that we get out of it? So because of this entire automation, you don't have to dedicate effort required to generate docs, to have like code generation or create mock tests and so on. All these can the async API spec that we create can be leveraged for this purpose. So, and another best part is, on top of all that, async API is trusted by multiple enterprises like Lego and many more. This validates the power of async API. Now, moving on to the next slide, let's talk about all the challenges that we face because of that. Now, what's actually given that we understand how how important is async API and how useful it is, we just want to think about why we are not able to implement this completely, or what is stopping us to do that? Now, what happens is, let's say you get started with async API. The main issue that people face is that having this just a doc mindset, where we come from a place where we have used Open API, we have used Swagger and all that. So we have this mentality that the async API will be just a documentation perspective, or where we can have the initial APIs drafted, and so on. But the real value of async API is to be an infrastructure defining config, and not just a descriptive config that we do once we have planned, or the stuff that we do just to get started on a particular API design. Treating it as a spec first tool unlocks automation, like code gen, mock servers, security enforcement, and so on. So let's talk about the API drift that happens. So many user treats async API as a draft pad and not as a source of truth. So without validation, versioning, and enforcement, it loses out on the trust, and the drift kicks in, which means, like, after a point, there is so much of gap between the actual implementation and the async API spec that we created initially, is that spec becomes completely useless, as you will not be able to rely on that, on what's the current state of the event driven architecture that you have created. Now, talking about security and governance, these two are like one of the most important aspect of event driven architectures. And what we have seen happening is, when people get started with async API, there are options to define protocol specific schemas, protocol specific security schemas, and so on. Like, for example, if you are trying to define a HTTP spec, you can define JWT tokens. And let's say if you are trying to define security for Kafka, you can define SASL mechanism and all its parameters, and so on. So async API has this ability to be very protocol specific as and when required. But we have to be very mindful when we are creating this spec, that the information that we have crafted in the async API spec actually you know is actually matching with what we have done actually in the implementation, so that there is no gap, so that there is no skip, and the spec can be used as it is for any sort of infrastructure deployments. Now, as we have seen earlier as well, that real world event driven architecture is never one protocol. It can ranges from Kafka to MQTT to WebSockets and HTTP, and all these coexist together as part of one single deployment. Now, when we talk about maintaining async API spec for one particular system, that seems pretty doable. But if you know about event-driven architecture, it consists of a lot of different pieces to make this entire architecture come together. And maintaining async API spec for individual modules or individual components is very difficult, and it has a significant overhead in terms of effort. Now, just to show you, this is a very typical example of an EDA setup, and as you can see, this is complicated enough for creating and maintaining async API for individual components, to define the interaction between each components, and so on. Just to help you understand, like one simple use case, let's say we are talking about IoT ingestion and control. So just for that one single use case, you have to have these many modules implemented. Some are available on market, some is done as a custom solution based on your requirements and so on. So what happens is, as more and more custom stuff comes into picture, it gets it gets very challenging to accommodate all these implementation, whereas also having in sync with the async API definition. So how do we solve this solution, right? We have talked about all the challenges and so on. Now what I wanted to introduce here is this open source project called Zilla, which is a multi-protocol edge and service proxy. It is designed to streamline, secure, and manage event-driven architecture effectively. So Zilla is a declarative and a no-code solution, and it is a stateless solution and does not allocate objects on its data path, making it super efficient. Now, if you look at this architectural diagram, and if you remember what we have seen in the previous slide, this is a very far more simplified and effective architecture, right? Where you have your consumers on your one end and you have your streaming platform, which is Kafka in this case, on the other end. You also have supports for observability in terms of various exporters, and you also have support for the schema registries to add data governance around your use cases. Now, one of the best part about Zilla is that it has a first class support for async API, so that you can leverage your spec directly and streamline the entire process of using the async API as a config to to automate your infrastructure deployment, which means like let's say you have a async API spec for HTTP on one of your use cases, and you have async API spec for Kafka on the same use cases. So you are maintaining these two spec. Now, what we can do at Zilla is you take both of the spec, deploy or pass them to Zilla. Zilla can process and do the mapping based on the operation mapping that we have done on the Zilla YAML, and create HTTP endpoints that will directly help you communicate with Kafka. So for your user, the experience will be very HTTP based. Let's say if you have a UI, or if you have a web browser, or if you have a mobile app, which where you want to have users to keep receiving recent updates on one particular topic in Kafka, this can easily streamline this entire use case by just allowing the spec to be used by Zilla and getting the deployment done. As you can see in this architectural diagram, is the number of moving pieces are very less. Zilla itself is a very powerful engine, and the the one of the most interesting part about Zilla is that it understands all the protocols natively. Like, for example, its understanding of Kafka wire protocol and HTTP and MQTT and gRPC is all native. We don't use any third-party library to rely and to communicate with let's say Kafka, or communicate with a HTTP server, or communicate with a gRPC server, and so on. So how does this help us, right, to have the understanding of the protocol natively? Is this helps us, first of all, to utilize the potential of the protocol without being restricted with what the client libraries have to provide, but also helps us do the mapping very at a very fine level, that when we have a HTTP request come in, we exactly know how do we do the mapping between HTTP to Kafka, or let's say MQTT to Kafka, and so on. So that's like one of the main advantage of having the understanding of the async API, having the understanding of the protocols natively. Now coming to the production readiness. So as I mentioned earlier, to have a solution is only is only useful to us is when they address all your production challenges, right? And Zilla has addressed all the checklists to be production ready solution, and it is also trusted by multiple enterprises for their EDA needs. So Zilla has integration with uh, multiple identity providers and ADs, and can have protocol specific config. Like for Kafka, if you want to define MTLS, or if you want to configure SASL as one of the security mechanism, uh, is this can easily be accommodated by Zilla configs. Also, in terms of data governance, Zilla has integration with all the major schema registries, which makes it possible to kind of leverage the one single schema registry where you can define your schemas, and that same schema can be used across protocols without the need to define it at individual level. So how does this helps us? So once we define a schema at one level, it is almost consistent, and there is no challenge of redefining everything. And once there is a evolution in schema, we have to make sure that every module that was using that schema has been updated and all that. That will not be a problem here, because Zilla relies on a schema registry and can, once we have received a new schema, or we have detected that a new schema has been have been updated or posted, uh, we will immediately start using the new schema across protocols without the need to kind of going through individual modules and modifying stuff. In terms of scalability, so how Zilla generally works is it starts an engine per core based on the number of cores on an instance. This makes both horizontal and vertical scaling possible. Like if you want to have just a single instance, you can keep adding additional cores, and the processing power of Zilla will be more, depending on the number of available cores. Zilla is also stateless, which means you don't need to bootstrap stuff before you get started with Zilla instance. So if you keep adding new instances and deploy Zilla on additional instances, still like you can scale completely without the need to have a complex process of going through individual uh, you know um, modifying this entire process of bootstrapping stuff before you can put in deployments, or you can use the new instance. So in case of surge in the traffic, you can automate based on metrics that are exposed, so that it is auto deployed. You can rely on, let's say, any of the auto scaling mechanism, and rely on particular metrics that once you have crossed this threshold, additional instances of Zilla can be deployed automatically. So now let's check out a demo where we will see how easy it is to get a async API spec running, and within minutes we will move from having a async API spec to actually full-fledged working system. So let me share my screen. So as I mentioned, Zilla is an open source project, and if you check out the Git repository, you will find that there is an examples directory under the Zilla repo, and we have curated um, all the real world use cases that can be achieved by Zilla, and we have a simplified way of running this. We have used Docker Compose for this. Zilla can also be installed using Homebrew, Helm. We also have support to run Zilla on AWS environment through ECS and so on. Zilla also has an enterprise version which enables you to run through, run this as an AMI and have curated solutions for different use cases like web streaming and IoT ingestion and so on. So let's get started on this demo. As you can see, the directory structure is very simple. You have a compose file where we have defined all our service like Zilla, Kafka, and so on. And the interesting part is this spec folder where we have a HTTP spec, which defines all your endpoints and channels and messages and schemas and so on. And we also have the Kafka async API spec where we have defined all the topics, the operation that's allowed, whether it is send or receive and so on. And if you look at the Zilla YAML, here is the place where we have done the mapping, which is API ID versus the operation ID. And one more important point that I wanted to share at this point is Zilla YAML is a very very declarative config, which you can use to directly define all these HTTP and API specification with or without the need to actually define the async API spec, which means in case you directly want to define your HTTP endpoint and map it to a Kafka topic, that can be done as easily as you can see here. So there is no hard requirement to have your async API defined, but it is always good to have async API defined for the EDA use cases so that it can be leveraged. And you don't have to keep redefining stuff again here on Zilla YAML and on your async API spec. So I'll just go ahead and run this. So I've already started this compose stack, and if we check out the Docker, you can see that we have a Zilla service running, and you can see we have a Kafka service running. Now let me just go ahead and trigger a So as you can see here, this is like a Kafka UI that I have used for this example to show you. These are the Kafka topics that we have. Now, let me try to just produce a message on trigger a like HTTP request. So I'll be using this curl command to create a pet entry in using /pets endpoint. As you can see, I've received 204, and if we check in the Kafka UI, you will see that we have received a new message. Now, just try to understand this behavior from two perspectives. One is the user, and another one is from Kafka perspective. So from a end user perspective who just wants to interact using HTTP protocol, will be shielded away from all the complex implementation or Kafka specific stuff, so that they can concentrate on what's really important for them, and rather than getting lost on understanding what a topic is, what partitions are, and so on. All these Kafka specific stuff, which might not be as relevant for a UI developer, or let's say someone who is very keen on just working with HTTP endpoints and not trying to understand like the complete flow, what's going behind. And so if you want to abstract those implementation detail and have like an interface, this is like one of the easiest way to do this. Now let me trigger a GET request so that we can see our message back. So as you can see, we are able to fetch that request. So this is one of the most simplest example. We can add bunch of additional stuff on this depending on your use cases. We can have security enabled based on access tokens, and just to validate whether these endpoints are accessible by a particular user. You can add a schema definition to understand or to limit that no poison pill is going into your Kafka, because the validation needs to happen. One of the best part about having this Zilla in between is that it shields all your Kafkas or any other server implementation from actually have to face all these um, security side validation or schema side validation. All this is taken care by Zilla itself. So if there is a invalid message that's coming in that gets rejected at Zilla, rather than have to go to Kafka and then get rejected and come back. So this helps reduce the number of requests coming into Kafka directly without overwhelming your Kafka cluster and handling all these cases at Zilla itself. Okay, let me share my slides again. Okay, so these are the two specs that we have used. You can use AsyncAPI Studio to kind of visualize what we have done, and the example is available at Zilla directory. As you can see, this is a open source repository where we have added all these examples. So anyone who is interested can try this out. The way to get started is extremely easy. We have Docker Compose added for all these examples, and you can just get started. We have readmes available on in each of these examples to help you go through all the use cases, or how you get started with a particular use case. So being said that, we have completed this presentation. So if you have any question, reach out to us on Slack. We have a very active Slack community where we have users and developers and of Zilla interacting and discussing use cases, problems, solutions, and so on. Thank you so much for your time.